Okay, thank you. So hello everyone, my name is Raphaël Sauzet and I co-chair the SCOR working group for DBGC with John Sharp, that is here with me. We really thank you to join today for the first webinar of the series that we organize as part of this SCOR working group. So this SCOR working group is called 4DBGC and is about the coordination of the development of gridded four-dimensional data products from biogeochemical Argo observations. So we are 21 official members from 14 countries. And we have also external members that join when they are interested in the topic. And so as part of this working group, we have this webinar series that start now. And we really thank Bruno, Buongiorno, Nardelli from the CNR that has accepted to give the first presentation for the first webinar. So I will just start with a few slides to present the group and to give some introduction. So this group has the mission to facilitate the discussion and coordination among the different scientific communities around the development, the validation, and the distribution of the 4D-BGC products from observational datasets and with a specific focus on the BGC Argo array. So the goal of this initiative is to significantly enhance access and utility of BGC Argo observations through the 4D BGC products, and thus refine our understanding of ocean biogeochemistry, improve models and reanalysis products, and also finally inform policy decisions. So you have here the picture of the group that has done the first in-person meeting in Ocean Science meeting during February from this year. Here we wanted just to show that we are providing a web page from the BGC Argo website not to us, but to give access to the BGC Argo data products. So you have here an example for some of the products. And it's here the prototype of this web page, but it will coming soon. So you will have the access of the BGC Argo-based products from the BGC Argo website soon. Here it was to mention that we have a website for the 4D BGC group, where you can find the group information, the group activities, and also the upcoming events, for example, the next webinars. So you can go on this webpage to see the information from the working group. We will record the webinars and we will put it in a YouTube channel that is called the 4D-BGC working group. So you have here the link. And so you will have access to all the webinars from the series that we want to give. And for the next webinar, we will circulate a link, so a Google form to fill in to join a 4D-BGC mailing list so that you will receive the information about upcoming virtual webinars and other 4D-BGC working group events. So it will help to avoid cross-spotting emails because we advertise, but maybe you received a lot of mails. So thank you, and I leave Bruno to share his screen, and thank you to him to give this talk.
So do you see my full screen presentation? Yeah?
Yes, it's perfect. Yeah.
Okay, then thanks, Raphael, and thanks to the entire group for inviting me for this webinar. I'm very pleased I have a chance to discuss with you about the work we have been doing in the last years on this topic related to the reconstruction of for the ocean state, both looking at physical variables and biogeochemical ones. So today's seminar, I've thought it could be nice to show you different things actually. So I will make a very brief and simple introduction on the different approaches that I see to get to a reconstruction of the ocean state. And then I will briefly present you two examples of the work we have been carrying out within two European Space Agency projects. So looking at the algorithms and potential of new techniques. And then I will spend the last part of the seminar presenting you some work we have been carrying out within a European project, actually starting from for the reconstruction of particulate organic carbon that was developed by Raphael and Hervé in the past, and to look at the potential that these new data-driven products have from the scientific point of view. So very briefly, as all of you surely know, there can be very different approaches to the problem of retrieving for the ocean state. And I'm listing on these slides just the ones that really give a lot of weight to observations, because of course also numerical models, they somehow implicitly include observations either in their setup, I mean, in using climatological fields or something, but actually the use of data is much more relevant when we either consider purely observational products that are based on the interpolation of in situ profiles. These are usually either lead us to climatological fields reconstruction or to the application of some statistical interpolation tool like the optimal interpolation. And of course, these kind of approaches, they can only give us information on either a sort of steady state of the ocean or on the dynamics that occur on very large scale and with low frequency. And of course, also the time series that are built by simply interpolating in situ profiles, they can be extremely unbalanced in the accuracy they achieve in the different parts of the world due to the sparseness of the data and to the different platforms that were launched over time. There's, of course, also the possibility to include observations through data assimilation in numerical models, which is quite a stronger approach with respect to simple numerical modeling. But of course, also here you can have advantages and disadvantages. One of the disadvantages when thinking about biogeochemical variables is that there's a lot of state variables, and too many variables are more complicated to handle during assimilation. And then there's also problems related to the fact that dynamics that is actually described the models does not always fully fits what is found in the observations. So there's considerable uncertainty, more difficulties to get a model that is close enough to the observation to allow an accurate and effective assimilation of the observations in the analysis step. But the approach I will be focusing today, of course, is none of the two above. It is related to the combination of different kinds of observations, and mostly not looking only at in situ observations, but also at the observation we can get from satellites, so remote sensing satellite data. And again, there's a lot of different specific algorithms that can be developed. The one I will be focusing today is related to what we call the 2D to 3D projection. So once we have 2D fields, we want to set up algorithms that are able to project the information we have at the surface to the deeper layers. even if we know that there's also hybrid approaches like the ones that first retrieve some kind of synthetic profiles and then combine the synthetic and the truly observed in situ profiles through statistical techniques or empirical techniques. And of course, there's a vast amount of different approaches that can be followed. Of course, there's some assumptions that are implicitly or explicitly made once we decide that the approach we want to follow is the projection of surface data at depth. One is that the deep processes must have a signal at the surface. And of course, this is not a huge assumption for both dynamics and I mean physical dynamics and at least the phytoplankton dynamics, because I mean air-sea interaction, they occur at the surface, the light comes from the surface, so it is not an uncommon situation to have dynamics that display some kind of response along the water column that is if not surface intensified, at least visible at the surface. Of course, we also generally assume that reduced order models or algorithms are sufficient to capture dominant dynamics, which is related to the fact that we only observe a few variables, and so we assume that these variables we have are sufficient to describe the 4D structure and the ocean state we are interested to retrieve. So, of course, once we want to combine satellite and in situ, an important step is getting to have consistent satellite data. I mean, surface fields that are reproducing at the same scales or as much as possible, looking at the same resolution, effective resolution. And but I'm not talking about these steps today because I will be focusing more on the projection algorithms that we've been developing and testing in recent years. And I will start actually, even if I know the group is biogeochemical focused first. I will start first from the work we have been doing within a European Space Agency project that is called World Ocean Circulation, where we were actually aiming to retrieve the temperature, salinity, and currents. But I take this as an example to show the different strategies that one can select when building a model for the projection at depth of the surface values. So what we did, well, I mean, our objective in this project was to retrieve actually a 4D reconstruction of a portion of the North Atlantic, and aiming to reconstruct temperature, salinity, and geostrophic velocities, which we may obtain as spatial derivatives of some dynamic heights. And then actually these data were used to carry out some scientific analysis, which are not describing today, but related, for example, to the assessment of the dispersal of eels larvae from the Sargasso Sea to the European coast, and also to look at the behavior of tuna fishes. So we had interactions with users on these topics. But today I will be focusing only on the intermediate step in our work, because of course we first had to collect or develop new products informing us on what's happening at the surface from satellite observations. Then we projected this data at depth, and then actually we applied other more advanced diagnostics to get also estimates of the vertical exchanges, for example, and so on. So just to show you the input data set that we used, there are sea surface temperature, sea surface salinity that has been built through that purely data-driven approach, combining in situ and satellite data, not only salinity observation from satellites, but also temperature salinity. So it's a multivariate technique. And then we have the sea surface elevation, actually the absolute dynamic topography provided through satellite altimeters. So these are the data that we want to project at depth. And the data that we use to learn how to do that are, of course, in situ profiles. And what we used is mostly profiles taken from Argo platforms and CTDs. We also used a climatology to work with anomalies with respect to climatology, because we tested in the past that it's much easier to learn how to reconstruct anomalies with respect to climatologies than to learn the full dynamics of the system. So anomalies are easier to learn. And we actually developed methods that are based on neural networks. So when dealing with this kind of networks, so what you need is to have a independent part of the data you have as independent test data. So we separated the data into a training test. Training data set, a test data set, and then actually during the training, the data are split again into what is really used for the training and what for the internal validation during the iteration of the methods. And then the problem can be set in very different ways, actually, because what we have is predictors at the surface. And we may have ancillary data as well. And we have our target variables that in this case were temperature, salinity, and the profile of steric heights, which is a proxy of the quasi-geostrophic stream function, actually. So there's some dynamical information here. And of course, the first possibility is just to try to retrieve the values at a specific depth, including the depth as one of the predictors. So we did some tests to see how efficient that was. And we built a network, a simple feed-forward neural network to start with, where each layer of the network is indicated here as a dense layer. And we verified that this kind of way to set the problem is not really efficient to reconstruct the full profile, because it is not exploiting really the shape of the profiles that we can learn from the in situ data. So this is not able to exploit the information, and it is also quite slow in learning. So a much better option is not to include the depth as a predictor variable, but to try to predict directly the full profile, having the predictor samples without depth. So this is the second architecture we tested, and this is actually able to exploit much better the sequential information. Of course, there's a lot of tests that need to be done when you want to set up a neural network, because there's many hyperparameters that one has to tune. So deciding how many hidden layers should be used, how many units within each hidden layer, and which activation function should be used in each layer, and so on. And of course, there's issues also related to the number of epochs that one should consider, and so on. But I'm not going to show any details on all the tests that were made, but I want to make a point related to a very interesting strategy to reduce the risk of overfitting, which is called dropout. Dropout, it's a technique that during training removes randomly a percentage of the neurons from the network, And when this is done during the training, this forces the network to generalize more efficiently, because it avoids the network to learn individual information routes from the input to the output. And the interesting thing is that the same approach can be used also during inference. So once the network has been trained, one can reconstruct, apply the network to predict the full profiles from the input data available. And by dropping some of the units all the times, you can get many different predictions of the profiles. And by this kind of sort of ensemble that you can build, you can also obtain an estimate of the accuracy of the reconstruction itself. So it's an approach that is equivalent somehow to Monte Carlo sampling. And it is interesting because it can inform us also on the accuracy of the network itself. So I'll show you just a few profiles of the root mean squared error that can be get using these methodologies. So here the retrieved profiles have been compared to on the test data. So they have never been seen during the training. And what we observe here is the error that is obtained with the different techniques. In this case, when using in green, you see a climatology. In blue, you see the methodology based on empirical orthogonal functions. And in orange, you see what the feed-forward neural network is able to do when using a single layer with 35 units. And that's not really nice because it basically has the same error as the climatology. But if you start if you optimize the architecture of the network to directly learn the profile and not the individual values for each depth, you start to see some improvements. And these improvements, they can be much higher if you increase the number of layers. So here you're using 2 hidden layers with 35 units. And they can also improve more if you increase significantly the number of neurons within each of the layers. But once you are building such a network, the problem is that you are using a lot of parameters. So a network with 2 hidden layers with 1,000 units each leads to more than 1 million parameters to be trained, starting from 35,000 profiles. So the degrees of freedom, they're not really so many. So what we thought could be an interesting test to run is to exploit a different kind of neural network, which is a recurrent neural network where in practice what we do is we sequentially train learn the weights in our hidden layer by transmitting the information from one depth to the other. So this is an iterative approach that is much more efficient in learning the information on sequential data, and it is usually applied to model time series or predict temporal evolution of variables. But in our case, what we did was adapting this approach and thinking about our profiles as vertical sequences. And so we designed a network that is, it looks a bit complicated. It is not that complicated in the very end, but it is much more efficient actually in extracting and learning the features that characterize the vertical profile. And indeed, if we look at the errors, just using 35 units per layer, we improve significantly with respect to a simple feed forward where we had thousands of hidden units. And so the big advantage is that this network only requires 16,000 parameters. And so this is what we have actually used for the remaining part of the project. Of course, all of this is already published and the codes are available and everything. And I can, I mean, if anyone wants additional information, I can be contacted by mail, no issues. Then we finally move to the application to biogeochemical reconstructions. So this is work that has been carried out mostly by Michela San Martino and by myself within another European Space Agency project, which is presently ongoing. It is called 4D MED. So this is focusing on the Mediterranean. And our objective here was to reconstruct the chlorophyll distribution in 4D down to 150 meters depth, so below more or less the base of the euphotic layer. And then there's been also work to use these in combination with temperature and other data to retrieve also an estimate of the primary productivity. And so what has been done was first of all setting up our in situ reference database, which is a collection of profiles obtained during oceanographic cruises, most of them on board Urania research vessel. But a big percentage of the profiles we were using, they are taken from biogeochemical Argo profilers. And there has been, of course, some work to get to consistent profiles in terms of quality control, sorry. We started in principle from around 14,000 profiles, but then the quality control ones were reduced to something more than 8,000. And concerning the surface data that we use for the projection, we started from what is available through the Copernicus, European Copernicus Marine Service, which is the part of the European program on Earth observation, which are freely available through the web. And so what has been done is we started from a similar configuration of the network that was used for the Atlantic case. There has been a test of slightly different architecture. So in the very end, the best performing algorithm includes some 1D convolutional layers. And it also includes, instead of the steric as we used to do with in the North Atlantic case, directly the density profile as one target variable. There has been, of course, work to tune the hyperparameters, but I mean, this is not really relevant for today's discussion. While it is relevant to show you one of the advantages of the neural networks that are usually considered a totally black box, while they can be used to kind of constrain the reconstruction to obey some physical laws. And this is done by selecting the proper terms in the loss function. So our loss function that is the function that needs to be minimized, that is minimized during the training of the network. So the parameters are optimized to get the lower loss function as possible. Our loss function is composed of 3 terms. The first one is basically a mean squared error loss term, which includes some different weights on the very surface and the very deep of profiles, because we noticed some issues in the reconstruction there, so we wanted to force the reconstruction to be accurate in these first layers. And the interesting thing is that through what is called a physical informed approach, we could also enforce the consistency between the density that is predicted directly by the network and the density that is obtained from the predicted temperature and salinity profiles, which is not given for granted if you use different kinds of models. So that's in practice, enforcing the network to learn how to reconstruct profiles that respect the equation of state. And the other interesting thing is that even if in reality we know that density inversions can be present in our observations, these are quite rare, and usually they can kind of lead to big issues when you want, especially if you want to estimate anything related to hydrostatic physics. So we also enforced the network to learn monotony, basically. So we introduce a term that forces the network not to include density inversions in the reconstruction, which is a problem that we know it's present in different kind of algorithms that are used, like multilinear regressions used for armored 3D reconstructions, for example, which is one of the products distributed by Copernicus. So just to show you some results. Of course, what you see here on the left is the errors computed with respect to the test profiles. So you see temperature, salinity, chlorophyll, and density errors. We don't have, in this plot, we don't have the comparison with other techniques except for, the box, red box here is showing you the errors that we got in the Atlantic, so it is not exactly comparable, but we see that at least we get the same order, the same kind of errors, both in terms of shape and of values. More comparable is the difference between what we get in the chlorophyll error, reconstruction error, and what was obtained by Michela in the past using a simple feed-forward neural network, and we are improving a lot with respect to this one. So the 3D reconstruction has been, it will be used, it's being used now to analyze different aspects of the dynamics in the Mediterranean. So there's work ongoing to analyze the biogeochemical provinces, looking not just at surface data, but also at what happens at depth. And just as an example of what can be seen in our reconstruction, there's this transect going from north to south across the Western Med, so crossing the Gulf of Lion area, which is an area well known for its deep water formation events that are followed in spring by very strong blooms, which are related, of course, to nutrient flux from the deep layers, and then restratification effects and proper light conditions in spring. So what we have in spring is a spring bloom that is of course observed very well at the surface, with deep mixing occurring in the northern part. And for example, in summer, we have a much more stratified conditions and the appearance of a deep chlorophyll maximum that we could not detect if looking only at the surface values measured by the satellites, because the satellites, they only observe the first meters, so down to the depth, first optical depth, so it's few meters. And yeah, so that's what we did in terms of algorithms. Yeah, as I told you, these chlorophyll and temperature data have been used also to estimate primary production. But yeah, and these data, actually, they are also already available through the project website. And but then I'm now finishing on the algorithm part, and I will move to the second topic I wanted to introduce, which is related to work we've been carrying out. We're still carrying out actually in the framework of the Atlanteco H2020 project. I missed to include the OGS logo here. Apologies. This is a collaboration between different people from different institutions. The work is now led by Marco and myself, basically. And the objective here is related to the estimate of the role of what is called mixing injection pump in the transfer of the export of particular organic carbon from the surface to the deep layers, because of course you know for sure much better than me how the organic carbon export pathways can be decomposed in different elements. So there's one very strong component. It's related to gravitational pump, so it's related to big particles that are sinking very fast from the euphotic layer to the deep ocean. There's migrant pump that is related to vertical migrating animals on both diel or longer time scale, but there's also a pump that is more directly related to mixing and advection driven, so they're more directly driven by physics. And this is what we have been focusing on. So what we aim to do was to estimate directly the carbon flux associated with the particulate organic carbon injection pump through what is called a kinematic approach. So if we consider the variations over the upper layer of the concentration of, in our case, POC, this can be described by an entrainment component, which is simply the variation of our reference depth. Very often it is what is taken is the mixed layer depth. So it's the variation of the mixed layer depth plus the flux through the mixed layer base that occurs both horizontally and vertically of the POC. Then, of course, one should or could know that there are also diffusion coming into play, and there may be also sources or unresolved scales that come into play. But what we've been mostly doing is actually estimating the role of entrainment, horizontal advection, and vertical advection of POC. And we did that actually testing different so-called depth horizons for the export, because very often in the literature, especially when looking at the gravitational pump, the export is just estimated as the flux across a flat surface at a fixed depth. So it may be 75 meters or 100 meters or something like this. But in reality, what is more relevant for POC is the deepest surface between the mixed layer depth and the euphotic depth, because this is where the flux of carbon leads to, blocks the biological activity, and where the consumption and degradation of POC starts. So we did different tests, and we started in this case from already available 3D reconstruction. So we used the temperature and salinity provided by, again, through Copernicus service by Armor 3D, which is a data-driven reconstruction at 1/4 degree resolution weekly. And starting from Armor 3D, within Copernicus, actually myself, I developed a product that through some diagnostic equations in the quasi-geostrophic approximation provides also vertical velocities and part of the geostrophic horizontal components. And so we combine these with the 3D POC fields that are provided by Raphael and Hervé. And yeah, I'm not going into the details on how Omega 3D is solved, but yeah, let's say that if you know the distribution of density and of geostrophic velocity in 3D, then you can in the quasi-geostrophic approximation write down an equation that can be somehow easily solved to obtain an estimate of the W. And so what we took was this global 3D POC data, which were still a bit gappy, even if they were provided weekly as well. So there has been a step to interpolate these gaps, and which was done through for a kind of extended EOF technique, iterative technique, which is called multivariate singular spectral analysis. And so we got all the data, and we could finally apply, sorry, I go back, just estimate these three terms, entrainment, horizontal advection, and vertical advection, either at the base of the mixed layer or at the fixed depth, or at a euphotic combination of euphotic and mixed layer depth. And so this is the picture that we got, where you see the total of the export related to this injection pump, and then how the different terms come into play in the different areas. And that's already interesting, because you can see how relevant is vertical advection, for example, in the southern hemisphere, and how relevant is the horizontal advection in the northern hemisphere at the high latitudes, for example. There's a lot of interesting things coming out, even if the numbers that are related to these estimates are quite low. So of course, here we are not including this calculation any sinking rate. So this is just the passive transport of POC that is considered buoyant in these calculations. And we compare these numbers with literature. So we are close to some of the values already provided. In some cases, we have much lower numbers. But the true advantage of our work is that we could provide time series of the export, so we can analyze interannual variations and also what is driving the export in the different regions. So we clearly related the export of POC in the North Atlantic, for example, to the formation of subpolar mode waters. So they occur in the same area. So that's part of the story that we found to be quite interesting, also because when you then look at global estimates and you look at the different latitudinal bands, then you realize that indeed what is most important is the Southern Ocean. And so we started focusing more on what is driving the time variation in the Southern Ocean. And one thing I want to also highlight here is that what you see on top is the estimate of the export over time based on the weekly data that we have. But if you did the same calculations using a climatological POC, you get much lower numbers and almost no interannual variability. So it's fundamental to be able to resolve the seasonal dynamics of POC to be able to assess correctly the export. And so we started to analyze also the relation between the variability we observe and some climatic indexes And specifically, we've been looking at the oceanic Niño index and the southern annular mode, and we have seen that we can explain a big part of what we observe with the combination, just a linear combination of these two indexes. And so basically this is it, and maybe I was longer than expected. So I come to the conclusions. The conclusions are very generic, actually. I think there's a lot of possibility to exploit new techniques, mostly the ones based on neural networks, and also to exploit the possibility that these techniques have to inform on the physics behind or some dynamical information we already have. And there's a lot of, and this is opening a lot of opportunities to do interesting science. Of course, there's a lot of requirements that are related to issues we still have on the data. We need a lot of data to get to be able to do robust training. We need consistent quality control, and we still have a lot of issues also on the satellite data side, and yeah, we are progressing on many aspects. And then concerning the application of deep learning techniques, there's still very few experiments and tests that are carried out. The number is increasing now. I may say not always starting from well-posed problems, because sometimes I've seen many papers where people are setting networks to learn from already interpolated Argo data, which means that a neural network would learn only how to emulate an interpolation, a classical interpolation algorithm, for example, which is not really the objective in my opinion. And well, very often we still rely on limited computing resources. I'm speaking from Napoli, CNR. So there's still a lot that we can do by improving also on this side. And this is it. So I'm now open to respond to questions, if any. Yeah, I don't know if you want me to keep the slides on.
Yeah, I'd say just in case if you need to go back and reference them. Thank you so much, Bruno. Yeah. Gave me a lot to think about for sure. We have a couple questions in the chat already. So I'll just read out the first few that came in. So Prasanna asked, how did you arrange the input data sets in tabular form? And I think that was during the first part of the talk.
Yeah, I mean, the data we started from, we have taken them from the Copernicus service, where there's a thematic assembly center dedicated to provide in situ observation in a common format and with the standard quality controls. So, I mean, the data, they are just written and provided at regular depths. And if not, we just remap on a fixed set of depths that we want to look at. So I don't remember if the data we started from were already given at 10 meter, I mean, over fixed depths every 10 meters, or if we applied some kind of bilinear interpolation or a spline, more likely spline interpolation to have them on the same layers. But that part was for sure the easy part. About the computing resources, when we're speaking about training networks like the ones I've shown you, they are not really huge, the ones that are needed. So this can be trained also on CPUs. GPUs are not necessarily needed for this kind of problems. Actually, my comment on the last slide it was more related on work we are carrying out to improve the 2D surface data, where we then have to handle images and convolutional networks that are really demanding in terms of computing resources. So I see another question.
Yeah, I'll also mention that if other folks have questions, feel free
Okay,
to
yeah,
raise your hands.
there's I'll read the question. It's a comment and question. In the Copernicus POC product, there's also estimates of the uncertainties, and how do these uncertainties propagate to your estimates of the POC estimates? So honestly, in the first work we did, we didn't consider these uncertainties. But well, the paper is under revision on a nice journal, and one of the things that we were asked to do is to assess somehow the uncertainties, and the suggestion we got was to try to apply different algorithms to retrieve the POC. Because we just took the one that was described as the best performing by the data producer themselves. And so what we actually did, what we actually are doing, because we are revising this paper now, is we have applied other algorithms, because that product not only provides a POC, but also the backscatter directly. So we went back to the backscatter, and we are applying different algorithms. So we will get to a range of different estimates, and we can associate, if not a truly estimate of the uncertainty, at least an idea of the range of the values that you can get. Input data sets are for surface only. How did you arrange it for subsurface? And maybe this I was not clear enough when I presented the architectures. But what we do when we train the model is we identify couples of predictor variables and predicted variables, target variables, and the target variables are the full profiles. So the observed one available from the in situ measurements. So that's how it works. And then to predict, we only need the surface.
We have a hand
the conversion
raised
from BBP POC is also biased at depth, since it relies mostly from surface value. Is this also considered in the expert estimates? I guess this is maybe not considered, but I'm not, honestly, I'm not expert on how POC is estimated from the Argo, BioArgo profilers. So maybe Rafael knows better than me the answer.
Actually, I think that you already answered with the fact that you are trying to use other relationships. So
okay.
They are all biased, but I think it's kind of, yes, giving something on this bias.
Does intercalibration between satellite and in situ measurements matter? Usually we find some biases between them. Yes, that's a very good point, actually, because I think that this matters for sure. And because, I mean, we know that also for chlorophyll, the differences between what we observe at sea and what we have from the satellites can be quite relevant. But yeah, this, let's say that we leave this to the step of building more robust and accurate satellite data. So it is part of the problem, but it is not what was covered, at least by what I presented today. So on the ocean color part, I'm not working. I'm working on I've been working a lot on the SST. I've been working a lot on salinity, and now we are working a lot on combining different variables to get improved surface currents. So yes, it matters for sure. Yeah.
We've had a hand raised from Jerome, so go ahead.
Yeah. Oh, sorry, Jerome. We went through the questions first.
No problem. Yeah, can you hear me? Yeah.
Yeah.
Okay. Thanks a lot, Bruno, for the very nice presentation, huge work. I would have just a few questions on the first part, just a standard, very simple one about your split between training and testing tests. I was wondering if you are doing just a simple random split.
That's a good question, and actually,
because
I didn't.
if there is probably
Yeah.
some temporal degradation scale from one profile to the other. So
Yeah, I didn't give details on this. Actually, in the North Atlantic case, this was done in a very brutal way by just randomly splitting. But then in the Mediterranean case, the one where the biogeochemical variables were included in this work here, different strategies have been tested. So one of the strategy was, for example, to keep the profiles from one specific year out. So for sure, these were not correlated to the ones, I mean, correlated, they may be correlated anyway, but I mean, they are not statistically dependent on the rest of the data set. So that's a very, it's for sure a key issue because in any case, we feel that with such a relatively small number of profiles, we might be suffering overfitting of the networks anyway. So it might be that the issue cannot be solved, but at least we are trying to improve on the strategy to avoid overfitting as much as possible. So yeah, that's a good question.
Okay, perfect. Maybe split by platform also. But
this was also done, and yeah.
Just an idea.
The consistency, the issue.
We did some work and it was working better with split by splitting the platforms rather than.
I don't remember all the details because actually this test was done by Michela and
just no problem. You've already answered, no problem. And the question about your short term the LSTM. It's very interesting as a solution. How do you deal with the fact? I guess it's I understand this as a way to force some correlation. What happens, for example, close to the thermocline, where the gradient may be much sharper? Have you looked at this? I mean, is it performing equally in all layers? Is there more errors close to the thermocline, or how do you deal with this?
I think you can see this by looking at the profiles of the errors that are on this slide here. And of course, the maximum of the error is always where the thermocline or the pycnocline is located, actually. So yes, that's an issue. There might be other approaches to try to improve this, but by, for example, including, I don't know, atmospheric fluxes, for example, or something like this. But there's so many possibilities and so many choices that we have not tested.
No, but it's a very nice choice, very nice idea to and the reduction of parameters is impressive. Thanks a lot.
Thanks.
All right, I think questions have slowed down and we're right at an hour. So yeah, let's all thank Bruno again. Thanks so much for the presentation.
Thanks a lot to you.
And thanks for all the participants for coming.
Thank you, Bruno.
Thanks to you.
And I must thank Giorgio who proposed Bruno's name. So I believe Giorgio is also attending. Thank you so much. There was another question I didn't notice. Was that answered? And in the end, John, did you see that? The intercalibration between satellite and in situ measurement?
Yeah, I think I covered this. I was just going to add about this, that also intercalibration between different platforms in situ might be an issue because I don't remember all the details, but we noticed some differences when training only with BioArgo or with BioArgo NCTD derived quantities. So yeah, that applies to not only to satellite. Yeah.
Okay. Thank you.
Thanks again.
Yeah, thank you.
I look forward to follow the next seminars then. I didn't know I was the first of the series. I'm very honored.
Great job as the first speaker.
Really,
Okay.
thanks a lot.
Thank you,
Thank
Bruno.
you. And bye-bye.
We'll be in touch. Bye-bye.
Yeah,